Welcome to Statics and Strength of Materials, Lecture 7. In this lecture, we're going to go through additional examples. In this example, we want to determine the resultant moment of the four forces acting on the rod. We have this force, and these two forces. And the idea is to find the moment about O. In this example, it's very clear that the 60 newtons goes through point O, and so it's not going to cause any moment. The 50 Newton force will cause a moment about O, so it's 50 Newton times 2. And the moment is into the page. We also have this 40 Newton, which is at a distance that we can calculate by finding out the distance between this point and this point. And so for that, we can use trigonometry to figure out that distance. We also have this distance, which is 4 meters, plus this distance will give us the total distance required to multiply by 40 in order to be able to determine the moment contribution. We also have this 20 Newton load. We have to find this distance. Again, use trigonometry to find this height. We know that this is 3 meters and this is 30 degrees, so we should be able to find this height. With that information, I have 20 meters times that distance, and that will give us the total moment that these 20 newtons will produce. We can add all these numbers, and we'll then in this manner determine the moment due to these four forces. Here's yet another example of a tree which is attached to a truck by a cable. We know that the force is 2 kilonewtons in that cable, and we want to express find out the moment due to this force F about O. The first step is to determine the position vector, and that position vector can be pointed from point O to B or from point O to A. In either case, the position vector to point A can be quickly determined, and that's 12k hat because the height is 12 in the Z direction. Or we can use point B, which is 4i hat because it's 4 meters in the X direction, and 12j hat because it's 12 meters in the Y direction. So two different vectors could be used. The force vector F can be expressed by determining first this unit vector that goes from A to B. And so we know the coordinates of this point, the coordinates of this point, so therefore we can find the position vector that connects A and B. Once you have that, you can divide the amount by the distance between point A and B, and that will give us a vector, a unit vector along A and B. Multiplied by the magnitude of 2 kilonewtons will give us the force vector and their components I, J, and K. Once we have that information, we can now calculate the moment by taking RA cross F or RB cross F. We should get the same answer regardless. And you should get the same answer as you can see here. In this example, we're going to examine two forces acting on a rod and to determine the resultant moment they create about the flange at O. So again, create a position vector from O to A and a position vector from O to B. You know the coordinates of point A, you know the coordinates of point O, you know the coordinates of point B, and so now you can determine a vector that goes from O to B or O to A. We should now be able to take the cross product very readily because we were given the force vectors and their components very quickly. So we should be able to determine the moments straightforwardly. And here is the position vector A, position vector B. Take the cross products of RA with F1 and the RB cross F2. And then after we operate, we get the moment for this problem. In this example, we want to determine the moment of the force about point O. Here, we could decompose this vector, so it's going downwards and to the right. Decomposing this vector to the right is 5 kilonewtons times cosine of 45, as you can see here on the right-hand side. And then the vector that goes downwards will be 5 kilonewtons times sine of 45 degrees. With that information, we should be able to determine with trigonometry the height from point O, the distance between point O and the line of action of Fx. We should be able to determine the distance between Fy, the line of action of that, with the distance from point O to that line of action. So that will give us a moment required by multiplying 5 kilonewtons cosine 45 times this amount, and then 5 kilonewtons sine 45 times 3 cosine 30 degrees. So that will be the process in this case. And then here we did the operations to show you how it's done. There are other ways you could solve the problem. Again, you can decompose a vector so that it's perpendicular to this rod, and then you will have another small vector from decomposing it to along the x-axis. And when you do that, you realize that goes through a line of action O, point O. So therefore, this small load does not cause any amount of moment, while this one does cause a moment. And so then you have this force times that distance, and that will give you the moment required, or the moment at point O due to that force. Example 26, we have a force that acts at the end of this bracket, and we want to determine the moment about point O. Again, you can resolve this force in the x direction and the y direction, as shown here. Once you have that, this distance, this distance. So all you have to do is to multiply 400 sine 30 degrees times 0.2 and 400 cosine 30 degrees times 0.4 to get the moment about O. And that's how the solution was developed here. The second analysis is to use vector analysis. You can draw a position vector from point O to this point and then calculate the cross product of R cross F, which was done here. And you will see that you will get the same answer as the scalar analysis, 98.6 in the Z direction into the page, and which is the same answer we got with the scalar approach. In example 27, we want to replace the force and couple system that was shown here by an equivalent resultant force and couple moment acting at point O. So how do we do that? So we can decompose this force into the x and y direction, and this force into the x and y direction, and then determine the equivalent force and the moment acting at point O for this system. To do this, we realize that in this case, all the forces can be added. That's one approach to solve the problem. So we sum all the forces in the x direction, all the forces in the y direction, and so we get the magnitude of the resultant force in the x direction and y direction. We can calculate the magnitude by taking the square root of frx and fry. Once I get the magnitude, I can get also the angle that the resultant is acting. And here you can see that we found the resultant, which was 8.58. You can see that here. This will be 8.58 at an angle of 49 degrees. We now had to find basically what moment is caused by these forces. And you can see here that these forces will cause a moment. And so that's a straightforward analysis, because all we have to do is determine the distance between this force and point O, this force and point O, and so forth. And there's 4 different forces, so I should have 4 different kinds of 4 terms. And I should be able to determine the moment due to these forces in a straightforward manner. Here we have yet another example, which is to replace the force and couple system acting on the member and by an equivalent force and couple moment acting at point O. So that's the question being asked. How do we achieve that? Again, we want to determine what force, equivalent force and couple moment should be acting point O so that the systems are equivalent. Well, the first step, again, is to add all the forces together to get there. And that's exactly what we've done. So decompose this force into the X and Y direction, and then sum all the forces in the X direction, all the forces in the Y direction. And then once you do that, you can calculate the magnitude of the force and then the angle, how that force is acting. And then calculate the moment should be a fairly straightforward approach. One thing we notice is that this force and this force forms a couple. So that's 200 newtons times 1 meter. A couple is a free vector, so you can put it on O if you want. And that's exactly what was done here. You can see 200 newton meters contributes to the moment. You have these other terms, and that follows the same approach we discussed. If I have this force and I have this distance, I know what's moment. The moment is that distance times this force. We can then decompose this vector into 2 x, y components. The y component times this distance will give us the moment for that. And then the 500 newtons decomposed in this direction times 1 meter gives you the moment about O. And you can see here again, all that has been calculated and provided. Another example that we have here is we have a structural member that is subjected to a couple moment M and forces F1 and F2. So I have this force F1, I have this force F2, I have this couple here that's acting in this particular direction. And the question is to replace this system by an equivalent resultant force and couple acting at this point O. So very simply, what we have to do is add all the forces together. And you can realize here that F1 is fairly straightforward. It's 800 newtons times K hat because it's going downwards in this direction. However, F2 is a little more tricky because they only gave you the magnitude, but you can calculate the direction by finding out the unit vector that goes along this direction. To determine that, we can find the coordinates of point B and C, and then using that, we can form a unit vector. The unit vector times 300 newtons gives you the full vector that we want for F2. The moment can also be found. We know the slope, so we should be able to determine basically the vector moment M that describes this couple. Once you have that, add all the forces. So add F1 and F2 to get the resultant, and you can put that here at the bottom directly. So we have all the components of that force. And then you want to do a moment summation to come up with the equivalent couple. M is the one that was acting here at the top over here, and we found what that was. And then the moment, the other moments are simply RC cross F1 plus RB cross F2. And that's simply a position vector from O to B and a position vector from O to C. And that will give us what we need to perform these calculations. And the moment is provided here for this analysis. Example 30 is to replace a force and couple moment system acting on the beam. So you have this beam and by an equivalent resultant force, and find where it is in the line of action that intersects the beam. Measure from point O. So where does this force go to make this work? Notice there's a couple here, 15 kilonewtons times meter. You have these forces. So again, how do we achieve that? The first step is to take all these forces and decompose them into the X and Y direction, add them up, and when we do that, we find the resultant force, and then we can determine the angle. And we find here that in the X direction is 4.8, in the Y direction is 2.4. The magnitude is simply the square root of the squares of these squares added. And then the angle theta can be found as a tangent inverse of this divided by that. And then now you have found the components of that force, but you don't know the distance from point O yet, because we want to find an equivalent, a distance that will give an equivalent behavior as the one on the left. To do that, we're going to say that about point O, we want to find the distance about point O. We want to see the two systems are equivalent if you find the moment about a point and the moments are the same. So for this system, the moment about O is this X component does not do any moment about O, but this force does create a moment about O, and it's 2.4 times D. I don't know what that is. That has to be equal to 4 times 1.5, and this component in the Y direction times 4.5. And then you have to also add this moment. When you do that, and you do all your calculations, you can determine the distance D that will have the same behavior for two systems. They're equivalent. Here is example 31. In this example, so here we have various forces being applied to this plate. The question is, what is the magnitude and direction of this resultant force that will give an equivalent force system as the one here? So as we can see here, the force resultant is simply a summation of the forces in the Z direction. So that's that's basically adding all this stuff up. When we do that, we find the summation of forces should be 1,400 newtons going downwards. So that will be that force resultant. The next question is, where should I place this so that the moment in this system is equal to the moment in this system? So I could select a point here that when I do the calculations, it will be simple to find out the moment. And so to do that, I could take moments about the x-axis. If I do that, you can notice here that I don't have to worry about the x-axis here because these forces go right through the x-axis. So all I really have is to take moments about the x-axis for each of these forces. So Fr times this distance is y, 100 newtons times 5 meters, and then 400 newtons times 10. And so that should be a simple calculation. So the moments about the x-axis is 1,400 newtons times y, as given here, and that has to be equal to the moments produced by these two forces, because these two go through the x-axis. So once you do that, you can find the distance y. You can, in a very similar way, find the moments about the y-axis. So these two forces don't produce any moments, but these two do, and that has to be equal to the moment about the y-axis for this force Fr, so Fr times x. I know Fr, which is 1,400 newtons, and so that will give me the value of x equals 3 meters. So now I know where to place the force resultant Fr, so that it gives me an equivalent moment as the one on the left. Here's yet another example of three forces applied to this system here. These three forces again can be added up. I want to find the equivalent resultant force and determine where it should be applied. So these simply summing forces in the z direction, and when I do that, I get the 700 pounds in the z direction. So that's why I have a k hat. So it's definitely going downwards. The question, where should it go? So I can put it a distance away somewhere. I know there's a summation of moments. So what I can do is some moments about O in this system, and then some moments about O in the equivalent system. And they have to be equal. So the summation of moments, so if I say that this is a distance x, this is distance y, then the position vector rp is xi hat plus y j hat cross with this force that I found, the resultant 700 k hat, and that has to be equal to the moment for a position vector ra cross fa, rb cross fb, plus rc cross fa. And so once I do this calculation, I can solve for x and y very readily. And you can solve for x and y, and then determine that these two systems are equivalent to each other. By doing so, we have concluded this particular example, and we will now then continue to a new topic in the very next lecture. So thank you for your attention, and I hope you understood the concepts.